All right, so we will get started with our second lecture here. As always, if you have questions during this, feel free to put it in the chat box. If you don't want to talk to everybody, you can send me a private message and I can also respond to you like that as well. Otherwise, let me pull up the PowerPoint and share that with everybody. All right, so I need to go back just a slide. All right, so I just want to do a super quick review of what we covered just to refresh yourself. So we were basically just going through a giant review of stuff we should have learned in other classes just to refresh our minds. So we looked at the functional groups. We looked at basic monomers that make up biological molecules. We looked at the basics of a prokaryotic, eukaryotic cell, and we talked about the basics of evolution. And then we ended here talking about enthalpy and entropy. That is the basics of thermodynamics. And so we're actually going to jump right into a question as I explained this slide on Monday. And, oh, we covered this question, sorry. So this was entropy chaos. There's a question after this, though, that I want to jump right into. And that has to do with spontaneity. So here is another, there's 3 questions, true or false. So I will bring up another poll so we can get our ideas on this. So just 3 true or false. 1, a spontaneous process always happens very quickly, true or false. A non-spontaneous reaction will proceed spontaneously in the reverse direction, true or false. And a spontaneous process can occur with a large decrease in entropy, true or false. So take your best guess on these 3 true and falses, and that is where we'll start. Again, these should be anonymous, so if you're not sure, take your best guess, try to logic it out. We'll do like 20 to 30 more seconds. Have a couple people still waiting to answer. All right, so let me share the results with you. So first off, spontaneous process will always happen very quickly. That is false. If you remember at the end of Monday, I said thermodynamics and kinetics are completely separate. Thermodynamics will tell you if something will happen. Kinetics will tell you how fast something will happen. Those 2 things are not connected. So just because something will happen does not mean it is going to happen quickly. For example, the sun is eventually going to engulf the earth. That is going to be a spontaneous process. That's not going to happen in anyone's lifetime. So that is not quick at all. Right. B, a non-spontaneous reaction will proceed spontaneously in the reverse direction. We have a question here. You're going to jinx it? I don't think I am. A non-spontaneous reaction will proceed spontaneously in the reverse direction. Seems we have a little bit of a misunderstanding here. That's what it's not what I like to see, but I'm glad we have these questions so we can discuss them. So that is true. let me get my pen out. All right, so we're going back to Gen Chem 2 here. We have a reaction. A goes to B. Just any random chemicals, any random reaction you want to think of. Delta G equals, let's say, plus 20 kilojoules per mole. All right, so that is a non-spontaneous reaction. But if you remember the rules from Gen Chem, if I flip a reaction where the product here is now the reactant, what happens is delta G, the sign changes. So that is a spontaneous reaction. Using something we can think about better than abstract A and B. So rusty nail goes to non-rusty nail. That's non-spontaneous. A nail is not going to magically unrust. But the reverse will happen. A non-rusty nail will rust eventually. So if something is spontaneous or non-spontaneous in one direction, that means it is spontaneous in the reverse direction, right? Let me go back to my poll here. 3, a spontaneous process can occur with a large decrease in entropy. True. So just as a reminder, delta G equals delta H minus T delta S. So if entropy has a large decrease, that means the delta S term is negative. Negative delta S multiplied by minus T means this whole process is positive, which is not good for spontaneity. But if the enthalpy is really negative, that means delta G can be negative. So it can happen. A process can occur even if order is being brought. The universe loves disorder, but as long as you give heat to the universe, you can pay for making order. If that was not true, nobody would be alive because we're very ordered beings. So all of the processes within us happens because we're ordering stuff for the most part. All right, so let's move on. And our last question for this PowerPoint until we go to the next PowerPoint is free energy calculations. So how can we use delta H, delta T, delta S? I will do A for us, and then I'll have you do B. Okay, let's consider a reaction. Our reaction has a delta H 15 kilojoules, 15 kilojoules. And our delta S is 50 joules per Kelvin. And I want to know if delta G is negative. That's what spontaneous means. Okay, so T is 10 degrees centigrade. A couple of things we need to change. One, the delta S, the units are in Kelvin. I gave you a temperature in Celsius. You cannot multiply a Celsius by a Kelvin. That is just crazy talk. You have to take your Celsius and turn it into a Kelvin. And to do that, you take your temperature, you add 273.15, but we can just say 273, equals 283 Kelvin. All right, so that's the first change we have to make before we do any calculation. The next is that we have 1 unit in kilojoules and 1 unit in joules. We cannot combine a kilojoules with joules. Again, that is just ridiculous. So the way to convert between joules and kilojoules, there are 1,000 joules and 1 kilojoules. Those of you who had me in Gen Chem, I'm sure you remembered how I love to make train tracks. Those of you who did not, this is the way I do any unit conversion. So 50 joules, joules are on top. I want to go to kilojoules. If something's at the top of the track and at the bottom of the track and it's the same unit, they cancel out. And I'm left with kilojoules. All right, now I just put in my conversion. Here's I didn't leave myself enough space, but that's 1,000 and that's 1. All right, so you multiply the top end of the tracks together, so 50 times 1. divided by whatever on the denominator. So you do 50 times 1,000, and what you should get is 0.05 kilojoules per Kelvin, if I did the math right in my head. All right, so now we can calculate delta G. Delta G equals delta H minus T delta S. So we have 15 kilojoules minus 283 multiplied by 0.05. And let me just calculate that super quickly, because I did not pre-calculate that for some reason. Okay, so this is 14.15. So 15 minus 14.15 is 0.85 kilojoules. This delta G is positive, non-spontaneous. All right, so I want you to try to do the same thing, but with ADC. Let me know if you think it's spontaneous or non-spontaneous. So if you have questions about what I just did there, you can send me a private message if you want. Otherwise, I'm going to give you a couple minutes to work on this, and I will put up another poll that simply says if you think it's spontaneous, non-spontaneous, or if you have no idea, just to get a sense of where we're at, how fast people are doing this. Again, these are anonymous, so if you are lost, I need to know so we can go over it a little bit. You can leave it in, so there's a question, do we have to put it in kilojoules or can we have it in joules? You can have it in joules. It does not matter. As long as both units are either both joules or both kilojoules, that works. You can put them in megajoules, millijoules, anything. All that matters is that they're the same unit. And if you are lost on this, feel free to send me like a private chat, and maybe I can help you out with that, what the confusion is, and I can type answers to you too, unless I feel like the question would be relevant, or the answer would be relevant to the rest of the class. All right, so there is a question on how we do the conversions again. So I will briefly go over that, and I'll write it right underneath the ADC. So to do these conversions, we need to know the conversion factor. So from going from joules to kilojoules, there are 1,000 joules in 1 kilojoule. That's basically the same unit. So if I'm given something that's 15 kilojoules. Here I'm going to do the reverse. I will go from kilojoules to joules. If I'm in 15 kilojoules and I want to go to joules, the way I have this set up is that on these train tracks, if there's a unit on the top and the same units on the bottom, they cancel out. So I want to cancel out kilojoules. So I know that has to go on the bottom, right? And I want to end up in a unit of joules. So joules should go on the top of this method. Now, I need to know what is the relationship between joules and kilojoules. I can write down the letters, but I can't write down the numbers. And so this is where that conversion comes in. There's 1 kilojoule in every 1,000 joules. All right. So kilojoules, I have one on the top, one on the bottom. They cancel out. Then you have 15 times 1,000. So you multiply everything at the top together, and then you divide it by everything at the bottom. So 15 times 1,000 divided by 1, well, that's 15,000 joules. And I'm actually going to end the poll right now. Looks like the majority of you who were able to finish this said yes. So that is actually correct. Yes, all these lectures are recorded, and you'll find them in the dated folders. So like the lecture from Mondays in the August 24th folder, you're going to find this one in the August 26th folder. And I post them on YouTube like right after I'm done. All right. So yep, majority of you said yes, that's correct. So let me just finish off this math. So we have, I'm going to stick with joules here. So 15,000, so that's my delta H minus T delta S. So 80 plus 273 is 353 multiplied by, here I'm already in joules, so I can leave this as joules, 50 joules per Kelvin. This is Kelvin. And if I did my math right, which you'll find out may not always be the case, I do make errors, negative 2,650 joules. We have a negative number, spontaneous. So as long as you have a negative number, it can be negative anything. As long as it's slightly negative, that means it's spontaneous. All right, so that is a little bit of our math section, and that ends our first PowerPoint. The answers to all these PowerPoints are also online. It should be up there now, and I also put up the answer to the study guides. They should be in a folder called Test 1, like with answers. But with that, I'm going to actually open up our second PowerPoint now, and we're going to jump right into that. All right. So let me pop this up. Okay, so. And we're going to continue on with thermodynamics because thermodynamics play a huge part in biochemistry. It is the chemistry part of biochemistry. And we're going to talk about equilibrium constants. Again, this is a throwback to general chemistry. So let's say we have a reaction of A plus B goes to C plus D. These little, letters, those are moles, right? So I probably should pick another letter, but like little A moles of A plus B moles of B goes to C moles of C plus D moles of D. We can write an equilibrium constant for that, where you take the concentration of your products, so C multiplied by D, so it's always products, divided by the concentration of your reactants, A times B. And for each of these concentrations, you raise them to the power of their moles, right? So for example, if this was 1A plus 2B go to 3C plus 1D, my equilibrium constant would be C raised to the power of 3 multiplied by D divided by A multiplied by the power of B squared. And these are just concentrations of A, B, C, and D at equilibrium, and that'll tell us when we're at equilibrium, what are the concentrations and what value could we expect to find. And we can relate this to free energy, where we have delta G equals delta G naught. So that's what that like zero is called. It's called a naught. Plus RT, R is the gas constant, T is temperature in Kelvin, multiplied by the natural log of KEQ. This will tell us under any conditions if a reaction is spontaneous, right? So inside the body, right? If we want to know if you're going to break down sugar, like everybody probably had lunch an hour or two ago, some of you maybe 4 hours ago now. And so your body will break down those carbohydrates, and if you're eating carbohydrates, or break down whatever you ate. And that will be spontaneous, and we can calculate how spontaneous based on this equation. Let's talk about this delta G naught. It's called standard free energy. And biochemists actually use the delta naught prime. That's how you pronounce that, delta G naught prime. And it's just a standard condition that everyone can agree on, where we just say for any reaction, if we're going to talk about delta G, we have to have a standard. And those standard conditions are a temperature of 25 C, pressure of 1 atmosphere, a pH of 7, and all concentrations are at 1 molar. All right, so that's just a default standard state people just agree on, so we can talk about delta G's together. Now let's say your system's at equilibrium, so our delta G equals 0. This whole slide is a long-winded way of saying how can we calculate standard free energy, more or less. And it's delta G naught equals minus RT ln KEQ. So this delta G, the one without the naught, that's like real conditions. This delta G naught is under equilibrium conditions. And we can calculate that with delta G naught equals minus RT ln KEQ. Again, you learned this all the way back in Gen Chem 2. It probably didn't stick, maybe not, but we will do some practice with this. And if you take Biochem 2 with me, we'll be seeing this equation a lot, because it has to do everything with metabolism. But we're gonna do some work to see if you remember how to do this. So I have an equation here, A. A plus B goes to C plus D at 25 C. Given those concentrations, given the gas constant, and given a temperature, I want you to calculate delta G naught for me. And then in B, I give you delta G naught. I want you to give me KEQ. So I'm gonna give everyone a couple minutes to do that. So in A, you're gonna give me delta G naught. B, you're gonna give me KEQ. As always, if you're not sure like how to go about this, let me know via chat. If you got an answer and you want to check that too, you can also send me a private message in chat as well. But I'll give everybody a few minutes to attempt these, and then I'll show you how they're done. And every equation should be in the top left that you need. So if you haven't made much progress on A yet, the first thing you should do for this is write down the KEQ equation. And so it's the same thing we just talked about. KEQ equals products multiplied together divided by reactants. And just as another refresher, the left side of the equation is always a reactant. The right side is always a product. All right, so KEQ equals the concentration of C multiplied by the concentration of D divided by concentration of A multiplied by the concentration of B. And so let's plug in numbers. C is 3, and you don't need to convert these since all the units are in micromolar. So C is 3, D is 5, A is 10, B is 15. All right, so we get that, and we should get 3 times 5 divided by 10 divided by 15. So KEQ equals 0.1. Then we need to take the natural log, the ln of this number. If you can't find your ln button, it's going to be on the same button that's either e caret or ex. It might be a secondary function of that. But we take the natural log of 0.1. And when we do that, we should get negative 2.3. So, and I'm just using this equation up here because I want to calculate delta G naught. So we figured out ln of KEQ, that's negative 2.3. R is a constant, so that's 8.314. Negative, so there's a negative sign there. So negative 8.314 joules mole Kelvin. Multiplied, so our gas constant's in Kelvin, so our temperature needs to be in Kelvin. So 25C plus 273, so multiplied by 298 Kelvin, multiplied by our natural log, negative 2.3. And when you do this, you should get a positive 5698.4. If I did my math right. You should definitely get a positive number though. So that means this reaction is not spontaneous, which makes sense because there are more reactants than products at equilibrium. A, there's a 10, B, there's a 15, C, there's a 3, and D, there's a 5. So if there are more reactants than products at equilibrium, delta G naught will be positive. If there's more products than reactants, delta G naught will be negative. All right, so are there any questions on how we went about A? Like, where did I get anything? All right, so I'm, for the sake of time here, I'm just gonna jump right into B. So B, I wanna calculate the equilibrium constant for this reaction. So delta G naught is minus 29. So minus 29 kilojoules per mole. This is equal to minus gas constant, 8.314. Again, I'm just doing delta G naught equals minus RT ln KEQ. Multiply by our temperature, 298 Kelvin, multiplied by the ln KEQ. Right, so in this problem, I want to figure out KEQ. So the first thing I'm going to do is divide each side by 8.314 times 10 to the minus 3. All right, you might be asking yourself, where did that 10 to the minus 3 come from? So our gas constant is in joules per mole Kelvin, while our delta G is in kilojoules. So we cannot combine something that's a joule with a kilojoule. So there are 1,000 joules in 1 kilojoule. So all I did was take the gas constant, divide by 1,000 to get my times 10 to the minus 3. Okay, so we do minus 29 divided by 8.314 times 10 to the minus 3 multiplied by 298. And I believe that should be like 11.7 if my notes are right. So we should get like 11.7 equals the natural log of KEQ. All right. So one thing I want to say about natural log, if you don't remember, is that if you have a variable that's being like held captive, or you're going to do the natural log of it, you cannot touch this variable until the natural log goes away. The way to cancel out ln, and it's the reason why they share the same button, is that you take the exponent of each side. So you do e to the power of each side. E to the power of a natural log, those cancel out. So you're left with KEQ. And e to the power of 11.7 is 121,177. So your KEQ value, your equilibrium constant, is 121,177. What does that mean? Why do we care about that? So the reason why knowing things like KEQ is important is that by knowing KEQ, you can tell me if a reaction is spontaneous. So if KEQ is greater than 1, delta G is negative, or delta G naught, I should say, is negative. If KEQ, whoa, I cannot write anymore. KEQ is less than 1, delta G naught prime, why did I write that? Is negative, is positive. So if KEQ is less than 1, is positive. While if KEQ is equal to 1, delta G naught prime, or naught is at equilibrium, so it's 0. So by knowing KEQ, we can know if something will happen or not. And inside the body, this is a big deal when it comes to metabolism, because the way enzymes work and the way your metabolic cycles work is that your cells are set up in such a way to take advantage of these KEQs and these delta Gs, and they will frequently combine something that's not spontaneous with something that is spontaneous to make reactions happen. And the way they do that, so let me just pause right there. I'm going to talk about proteins and cells like they know what they're doing, but just keep in mind they don't have like any thoughts. So I just like to personify cells and proteins. Anyways, continuing on. They will combine a positive delta G with a negative delta G to make a reaction happen. Again, we will see that if you take Biochem 2, but we're just going to get the fundamentals down right now. Right. So yeah, that's A and B. If you have any questions about that, again, feel free to send me a chat. And all these notes, all the answers will be going up online as well if you had a little trouble following along, or you can rewatch the video as well. One of the slight benefits of doing an all online class is that you can rewatch these notes unlike a real class. All right. Yay, done with math for the time being. So we're going to briefly talk about enzymes. To get into this class, you need to take organic chemistry. In organic chemistry, there are a lot of like different weird enzymes, because organic chemistry is weird. And anyone who likes organic chemistry has an interesting, they like interesting things. I'm just kidding. If you like organic chemistry, that's great. I don't. I should say I don't like it. It just wasn't my thing. All right. Anyways, enough knocking on organic chemists. So enzymes will catalyze reactions inside your body that otherwise would not happen at any rate that would allow you to be alive. So if you tried to like break down like a sandwich from lunch without enzymes, it would take a long time to break down, so long you'd be dead. Inside the body, we use proteins. Proteins are going to be your enzymes 99% of the time. Sometimes RNA will be a enzyme too, ribozymes. That actually happens when making proteins. Rarely, like there's a couple examples of DNA being enzymes, but that's super rare. And what enzymes do is that they will catalyze a specific reaction. And they're very selective because you don't want any random side reactions happening that will kill your cell. But what we're looking at here is we're looking at a free energy diagram. So the way to really read this is that here is the free energy of the reactants. Here's the free energy of the products. The difference between these two lines is the free energy of the reaction. From the reactants, so here blue is uncatalyzed, red is catalyzed. All right. So the energy from the top of the hill of the blue to the reactants is called delta G dagger. It's activation energy. How much energy you have to put into your system for a reaction to happen. And what an enzyme does is that it lowers the activation barrier. And so it is easier to make a reaction happen. And this delta G double dagger, that can be directly related to speed of a reaction by using some equations. So that's what an enzyme does. It lowers the activation energy. So I do have a question. It says unanalyzed. I never noticed that before. But between a catalyzed and uncatalyzed reaction, how is delta G different? And I'll give you a hint. The more negative a delta G, the more favorable the reaction. So let me pull up that poll. All right, there it is. So when you're comparing the delta G between a catalyzed and uncatalyzed reaction, is delta G more negative for a catalyzed reaction? Is it more positive for a catalyzed reaction? Or is there no difference? Keeping in mind that the more negative your delta G is, the more favorable the reaction is. The faster it will go, in other words. And if you're not sure, again, just take your best guess, best educated guess. I'll let this go for like 20 more seconds. All right. So let me share the results. So there's a reason why I kept saying, remember, delta G is more favorable, or the negative delta G is more favorable. That's because I was leading you down the wrong path. I'm sorry, I'm evil. So delta G does not change between a catalyzed and uncatalyzed reaction. An enzyme does not make a reaction more favorable at all. So look at the red and blue line here at the reactants and the red and blue line here for products. Delta G is the same. Delta G for a reaction never changes with an enzyme. All an enzyme does is that it changes delta G double dagger. All an enzyme does is that it changes the transition state or activation barrier. Basically, that's the same thing, more or less. But it lowers the activation barrier. That's what makes the reaction go faster. It will never, ever, ever change delta G. If delta G is fixed for a set reaction. So the answer is no difference. Sometimes I have to throw in those misleading questions. I guess I don't have to, but I should say I want to. All right. Now, we're going to probably get to, this is probably the most important topic in all of biochemistry, hydrogen bonding. If you're never sure what to put on a test, you probably have a 10% chance of getting something right if you just say hydrogen bonding. Hydrogen bonding, we are big bags of water, right? We are like 70% water. Hydrogen bonding makes life possible. If hydrogen bonding wasn't a thing, life as we know it would not be a thing either. And I'll get into that when we talk about proteins, why it's so important. But the thing you need to know about hydrogen bonding, only oxygen, nitrogen, and fluorine can be a part of a hydrogen bond. Carbon, if you have a carbon-hydrogen bond, or a carbon covalently bound to a hydrogen, that molecule will never hydrogen bond. All right, so what is a hydrogen bond? A hydrogen bond is just a non-covalent, so non-covalent. And if you remember from Gen Chem or organic chem, non-covalent means you don't move electrons. It's a non-covalent interaction between a hydrogen that is partially positive and a molecule that is partially negative. Here, water is partially negative near the oxygen and partially positive near the hydrogens. So what happens in hydrogen bonding, if it's between water molecules, the hydrogen of one water will orient in such a way to interact with the electrons of another oxygen. They form a non-covalent interaction. You have a positive next to a negative. That's favorable. Only hydrogens attached to oxygen, nitrogen, or fluorine, or only oxygen, nitrogen, and fluorine themselves are ever going to be in hydrogen bonds in biochemistry. Yeah, I'll just leave it at that. We're just going to keep it simple. We're not going to go into minute cases, but that is going to be our cases for us: oxygen, nitrogen, and fluorine. And to make sure we have that, I want you to try or you to look at these three molecules and decide of A, B, and C, which parts of that molecule can hydrogen bond? Which one can be hydrogen bonds, either acceptors or donators? And B, once you have an idea for that, I want you to draw a water molecule hydrogen bonding to 4 other water molecules, just so we are all on the same page of what a hydrogen bond looks like. Again, I'll give people a few minutes for this. As always, if you have questions, if you're lost, not sure what to do, just send me a chat and I'll be happy to respond. Oops. Remember, only the atoms NOF, nitrogen, oxygen, and fluorine, can be in hydrogen bonds. And for B, I would just start with one center water molecule and draw 4 other water molecules around that. And I'll do like a minute for people to finish up since we're running out of time here. And I want to get to these answers. That's the last thing that we do. All right. So A, we're just saying what parts of that molecule can hydrogen bond? Well, we have a hydrogen connected to a nitrogen. That can hydrogen bond. It's nitrogen. We have 2 hydrogens that are connected to a nitrogen. That can hydrogen bond. We have a nitrogen by itself. That can hydrogen bond. We have an oxygen by itself. That can hydrogen bond. We have a nitrogen, hydrogen bond. NH, hydrogen bond. So basically everything that's not a carbon can hydrogen bond in that nucleotide or nucleoside rather. How about B, our other nucleoside? NH2, that can hydrogen bond. An N, a water could come right next to this nitrogen as so and hydrogen bond to that nitrogen. Or it could come next to this oxygen and form a hydrogen bond with that. Or that NH, form a hydrogen bond. C, COO minus. You have oxygens can hydrogen bond. OH, you have a hydrogen connected to an oxygen that can hydrogen bond. NH3 plus, you have a hydrogen connected to a nitrogen that can hydrogen bond. Never, ever, ever select a hydrogen connected to a carbon. Never, ever, ever select a hydrogen connected to a carbon. That's the one thing I ask of this class. When we talk about hydrogen bonds, do not say carbon, hydrogen. Carbon cannot do that. All right, so one water molecule can bond to 4 different things. Draw it. Well, like I said, each, the oxygen of water is partially negative, hydrogen is partially positive. So one hydrogen bond can be from a water molecule to that part of the oxygen. Another hydrogen bond could be to the other part of the hydrogen. Then you have the hydrogens left over. So an oxygen could come from water, interact with that, or another oxygen could come, or another water could come with that oxygen and interact with that. So that's how hydrogen bond works when it comes to water. Partial positive, always next to a partial negative. And I think we will call it at that. On Friday, we'll finish up here. And I think, if I remember right, we should probably catch up on Friday of where, like, we should probably be at the end of PowerPoint 3 by the end of Friday. All right, so let me clear this. That will end our class, so it's 2:50. As always, if you have questions, feel free to email me. I will post another homework on Wiley Plus tool. So to get there, you go to Tools, Wiley. Remember, all homework will be posted after we do an in-class session, and that's all due on Sunday. The recording of this lecture, if you want to watch it again, will be found in the Wednesday, August 26th folder. Otherwise, Hope you have a good day, and I hope to see you on Friday. Take care, everybody.